The Rick Sulis Memorial Weather Station is located on the University of Waterloo main campus, located within the city limits of Waterloo, Ontario, Canada. The Waterloo campus is situated on the Haldimand Tract, land that was promised to the Haudenosaunee of the Six Nations of the Grand River, and is within the territory of the Neutral, Anishinaabe, and the Haudenosaunee peoples. The Waterloo campus is conceptually divided into two sections. The main and east campus, to the south of Columbia Street, hosts the majority of the academic units, student lodging, and administrative operations. The North Campus, to the north of Columbia Street, hosts additional academic units, an athletics and recreational complex, the David Johnson Research and Technology Park, additional lodging, a nature preserve, agricultural fields, and the Rick Sulis Memorial Weather Station. The weather station is situated on North Campus to the west of Warrior Field, the principal athletic field of the Athletics and Recreational Complex, and a small body of water referred to as Columbia Lake. The weather station is operated and maintained by the Department of Civil and Environmental Engineering within the Faculty of Engineering at the University of Waterloo. The site is referred to as a weather station rather than a meteorological station, i.e. a Class A designation, as it does not meet some of the criteria established by the World Meteorological Association and Environment Canada and Climate Change's Synoptic Weather Station classification. Namely, the site does not meet the following criteria. Established in 1997, the station has yet to meet the 30-year data recording period of record criteria. There is a small body of water to the east of the station, Columbia Lake, and a stand of trees to the northwest, which can create localized deviations in weather patterns, conditions, and parameters. For a Class A meteorological designation, surrounding land use, vegetation, communities, and topography must be relatively uniform for at least a radial distance of 250 meters from the monitoring station. The final criteria that does not meet the Class A designation relates to access to the monitoring station. In addition to measuring meteorological conditions, the station is also used for teaching purposes. Facilitated access is permitted to the site for the instruction of undergraduate and graduate courses in various faculties at the university. In addition, high school, public school, and community interest tours are also hosted and available. By furnishing such teaching access and limited by the other constraints identified, the weather station does not fully meet all the criteria to be considered a Class A meteorological designation. Now let's explore some of the monitoring and instrumentation details of the Rick Sulis Memorial Weather Station.
Welcome to the Rick Sulis Memorial Weather Station. It was founded back in 1997 by Professor Eric Sulis. He recognized a need for publicly accessible weather data. This station was one of the first stations that supplied free weather data to the outside world. The sensor itself, it consists of this tower with 12 separate instrumentations hooked into it. It is all run by this little data logger right here, successfully powered by a small solar panel above. All the sensors feed into here. There's the ADD thing in here, there's logs. But you'll notice on this side, there is a cellular modem. It actually then sends all the data to a website, and we just garnish it out and present it on the University of Waterloo Weather Station website. This is it. I'll walk you through the top. We have a wind speed anemometer on the one side, corresponding at that height. We have the direction of the wind is coming from. We drop down. In behind, we have the temperature RH sensors that measure temperature and relative humidity. In behind that, we have another sensor that measures barometric pressure. Then dropping down a little further, we have the two pyranometers measuring incoming and reflected shortwave radiation. We have the data logger itself. We have a second anemometer at the height of our precipitation gauge behind, so we can actually do some fine calculations to adjust for any lost precipitation due to wind speed. We have a Judd ultrasonic snow depth gauge, which actually, as snow acquires, we can get the depth of the snow. Buried underneath that at 20 centimeters is a water content meter. And over to this side, we have the tipping bucket rain gauges, which measures rain gauges that measure rainfall during the summer season. And it roughly jives. We can get it with the mass type current rain gauge you see behind. So This is the actual University of Waterloo weather station. All the data is recorded every 15 minutes. That's not saying it's actually being recorded continuously. We just present it on a 15-minute period. You can, upon request, get finer measurements. Like I said, we actually record every minute. The weather station itself, during the Pan American Games in Toronto, we actually transferred control of it over to the Pan American committee, so they can actually, then they were actually souped it right up, so it was sampling almost on a minute basis, sending it to Toronto. That way they could control events during the open air competitions. The instrument we have here is an Pluvio mass precipitation gauge. The reason it's called the precipitation gauge is in the fact that it actually can work in the winter to measure snowfall. The weather station will actually produce snow water equivalent in the winter, and what happens is inside here is a bucket, and we'll show you later, is a bucket with a mixture of ethylene glycol, methyl hydrate, and 2-cycle engine oil. What you also see is an alter shield here, which is actually at the top of the rain gauge. The purpose of it is to break up any upwelling and wind coming straight at, which would blow snow across the top. We'll now lift off the lid, and I'll give you an inside look at what the instrument looks like. So essentially, this is the mass flow gauge. This is a bucket which will capture about 300 millimeters of rainfall. What you see inside right now is the rain from the weekend, plus the pink color is the ethylene glycol. We won't be able to see the methyl hydrate, and then the slight green top thing is the 2-cycle engine oil, which stops the evaporation. So the ethylene glycol keeps it from freezing. The methyl hydrate will melt any snowfall that comes inside, melts it down, and the 2-cycle engine oil keeps it from evaporating, so we get a nice mass curve. All the electronics in here are done on a load cell. There's a little load cell there, which is an instrument that measures the weight, and as the water comes up, the weight goes up and it gets transferred over to the weather station data logger. This is the second precipitation gauge we have at the weather station. It is actually a rain gauge. It will only measure rainfall, so it is only suitable for when we can have rain. It is a tipping bucket rain gauge. So essentially, the rain comes in, goes through, and inside there's a little mechanism that will tip. The data logger at the weather station will actually record the number of tips, and from there we know that it will tip at either 0.1, 0.2, or whatever millimeters of rain. We count the number of tips, and we then, through an algorithm, come up with the amount of rain that's fallen. The nice thing about tipping buckets is they can actually, you can determine rainfall intensities, the amount it tips in a 15-minute period. The way it works is over 15 minutes we'll store that and produce that to the weather station, but you can then count the tips or the amount of rain in a 15-minute period and get the intensity. So again, it just comes out like this. Here what you'll see is a little screen that keeps debris in that from hitting the and getting stuck in the orifice. It also prevents any raindrops from coming straight through and tipping the bucket. This is essentially the inside of the tipping bucket rain gauge. You can see there's a little bit of 2 tipping buckets. As they go through, it flips a little reed switch. We count on, off, or 1 IO. It counts the number of tips. And again, this one is set for 2 millimeters per tip. So every time this tips, we know it's been 0.2 millimeters of rainfall. Again, it just runs through there, it goes underground and over to the rain station. So that is essentially the workings of a tipping bucket rain gauge. It just tips back and forth. I would tip this for you, but we did have some precipitation yesterday and it's partially loaded. So if we get any today, it could tip and I would throw it off by 0.2 and that would affect the readings. So that's it for the tipping bucket. What we have here is an older style of mass precipitation gauge. This is a Belfort. Again, it's a mass type. It weighs any precipitation. Again, you're allowed to, you can put in methyl hydrate, ethylene glycol, and that to convert snow to water. What it has on it right now is a knifer shield. Again, it's very similar to the altar shield. It's meant to break up any vertical wind currents or anything that comes across here. It allows the snow to fall in through this orifice here, which is an 8-inch orifice with the brass ring on top. It's very simple, and then it just drains down into the bucket. We'll now remove this knifer shield for you, and I'll take and give you a better inside look. So again, this is the top of it with the Belfort itself. Any precipitation comes in through here. What happens is, in this case, it gets collected in a bucket. And the bucket is actually complete with a piece of copper tubing that comes through. So, and when it fills and you don't have time to do maintenance on the rain gauge, any excess precipitation will go through the orifice and drain out safely and not damage your gauge. The way it works, it's like I said, it's an old inside here, and they've retrofitted this one. This one used to originally have a strip chart with a little pin. The chart would turn, and as the rain went up, so would go the needle. It was then retrofitted with a variable resistor on a gear thing. So you would actually supply a voltage to this. It would then, you'd get a known signal, and as the weight went in, the resistance would change, the voltage would change, and you would equate that to an amount of precipitation. This instrument is a cup anemometer, and it measures wind speed in meters per second. The way it works is, I'll just stop it here, you'll see that there's a little cup that grabs the wind, and it just starts spinning. So it goes around. Inside here is a little commutator, and it picks up the frequency. So it measures the frequency of the rotation. That frequency notation goes along here to the data logger, and the data logger then converts the frequency into a wind speed in meters per second. The advantages and disadvantages of these ones are the cheaper ones, or the more cost-effective ones, there's an inertial dampening. It takes so much wind to spend it. Like, so this one will actually needs 0.2 meters per second to actually get it to rotate, and there is an upper end of around 50 meters per second before it cannot be measured by the data logger. It's quite simple. It just spins in the wind, and the data logger then converts it to meters per second. I should mention that the data logger actually has, when we measure, this one measures continually, and we take the average over 15 minutes. It also has a capability in it to, it measures the peak burst, or the peak gust wind speed, and it'll save that, and we can actually send out a gust wind speed. So it measures it, but it also records the peak gust, and stores that in a separate algorithm. Up the tower, you will see another anemometer. Again, it's based on the same principle: a vertical axis, cup spinning on it, a little commutator inside picking up the frequency. That frequency is equated to a wind speed and direction. Now, the reason it's up so high, it is above the surrounding fence, and more appropriately, that's where you get the wind speeds. When the weather reports a wind speed of such and such, it's based on the upper measurements, so it avoids most of the ground influences, any upwellings and all that. It's just straight wind thing. It corresponds to, you notice this one is at this height as it is at the top of most of the precipitation gauges. That way we can actually equate for a shear wind atop the altar shield, and we can then back calculate if we're under catching precipitation, or we can get a true value and apply math to see, you know, that it's more accurate measurements of the precipitation. Again, the upper one is to measure the wind speed that gets broadcast out by weather people. It measures the actual wind speed, avoid of any ground influences, upwellings, screens, fences, other weather stations, anything around. And this one is particularly used to calculate catchment of a precipitation gauge. Instrument on this side of the tower is actually the wind direction or weather vane. It essentially is a wing or vane mounted on a vertical axis through a resistor, a variable speed resistor. So as we orientate it, when we set it up, we'll come up and we'll set, so 0 degrees represents 2.5 volts for, let's say, so we know that, we set that up, and as we come around, then the due south would be 1.25 volts. Again, it's just a vertical vane mounted on an axis around that. We send up a voltage, we orientate it to north, and then we just base everything down on a wheel of 360. The disadvantage of these is the resistor are going to give us a dead band. So we might set it up for 0 degrees, but when it comes around to 357, 358, 355, somewhere in there, it gets into that zone where we're not sure if it's back to 0 in there because the instrument won't be able to read it up. So that's the disadvantage. The more expensive ones, you can get a finer resistor in there, and you get a finer degree. You get tighter resolution on your degrees of off of north. Instrument we have here is a barometric pressure gauge. It works on the principle very similar to what you guys did when you were in grade 6 science and you did your weather unit. When you took a balloon, a skin, and you stretched over a tin can, and then you put a straw on it, and as the pressure changed, it went up and down. Essentially, that's all it is in here. There's a little diaphragm that moves back and forth as the barometric pressure changes on one side to the other, and that diaphragm is actually a displacement transducer. So as it measures back and forth, it sends a signal, electric signal, to the data logger, and the data logger calibrates that slight movement into barometric pressure. The next instrument I'm going to show you is the RH temperature sensor. It is actually housed inside this guild radiation screen. The purpose for that is it stops the sun from hitting it, or solar radiation from hitting the sensor and giving it an artificial high temperature. It also allows for shade and lets moisture in and out. So again, it just stops the stuff from the sun from hitting the sensors directly. The sensors themselves are, the temperature sensor is a thermistor, which is actually a little glass bead with a tiny wire inside. So that became, again, it's just a resistance measurement, and as the wire expands and contracts inside the glass bead, we equate that to a temperature, and the voltage will slightly change depending on the temperature. We know that temperature, and it gets recorded into the data log. The RH sensor is, again, it's like almost a little mirror inside an encapsulated thing, and its electric current is run through there, and we get condensation, and that condensation on the mirror from the humidity will then again change the voltage back and forth, and from there we can determine the humidity in the air. The next instrument I'm going to show you is actually, there's two of the same instrument here, are shortwave pyranometers. They essentially measure the heating or the shortwave radiation coming in from the sun, and also measure the reflected stuff. So this one will actually measure the shortwave incoming radiation, and the bottom one gets what's reflected back. And again, that all depends on the albedo that you're over. Under grass, it has a very low albedo, so 10 gets more absorbed into the earth. If we had snow cover here, that's a high albedo, or white, it would reflect it back, so we get a higher component on here. The net difference between them is actually the solar radiation, the heating component in watts per square meter. They work similar to a solar panel. The radiation hits here, it generates a little electric current, it goes into the data logger. That electric current and the millivolts will actually convert into watts per square meter and get a heating component. The limitations of these ones are actually on where they can actually measure the sun. If the sun comes down, and so in the evening, it tends to cut out a little bit in the later evening and the early mornings until the sun gets up and picks them up. So again, shortwave radiation pyrometers. Instrument you see here is a Judd snow depth gauge. The principle it works on is sound waves being sent out by a sensor down to the ground and coming back up. So what we've done is we put this in, we measure the distance to the ground to the sensor, we know that distance. As snow comes, it builds up, so the distance decreases, and we actually just do the calculations and we can actually measure snow depth. What you see inside this little white tube is a little temperature probe, because the speed of sound will change with temperature, so we actually can adjust for the speed of sound to get a true depth measurement. The sensor you see here, or rather 20 centimeters below my foot, is a soil moisture probe. Now, we located it at 20 centimeters is because that's the most important area that agricultural people look for soil moisture for crops and stuff like that. It works on the principle, it looks like a fork, or just two forks like this. So we dug down 20 centimeters, we drove it into the undisturbed face, that way we got an undisturbed soil moisture. We drive it in there, and then we backfilled. It works on the principle as we send an electric current on the one tong, and it returns on the second tong. The moisture in between that gap will vary the resistance, which will give us a voltage, and from that we can back calculate out the volumetric soil moisture. What we have here is an evaporation pan. It is 4 feet or 1.22 meters in diameter, 10 inches or 0.254 meters in depth. It has been decommissioned due to the seasonal change. We don't expect that much evaporation to happen through the fall and winter. It will happen, but it's minute. So essentially what happens is here, water is put into here to a certain depth. The depth is measured by a J-hook, or a little device that comes up like this, and it just breaks the water surface. We do that to prevent, as a J-hook, to prevent capillary action or tension on the hook pulling it up. We can get exact measurement. So essentially what happens, every day you'll come out and you'll measure the water. It's either above the J-hook by taking it out and measuring it, or by adding water, which will come up with the evaporation of the area. Again, temperature, the max min water temperature taken, so you can allow for heat. And again, it's inside the enclosure that you see. They're quite susceptible to animals coming in and drinking out of them, or you have to come and make sure that there's no debris, leaves that fall in. That's the other reason you take them out in the fall. It's just that you can't keep, it has to be a pure, clear water surface to work on. And again, like I said, it's quite simple. You just measure the amount of water above or below your J-hook, and you calculate that volume, and you can back calculate out the evaporation for that day.